Hello everyone, welcome back to ptet.chemistry channel. My name is Dr. Ant. In this tutorial video, we'll go through the structure and bonding kind of topical questions for these AQA A Level chemistry. So A Level chemistry are taken by students 16 to 18 years old advanced chemistry level. It is suitable for any 16 to 18 years old doing whatever curriculum all around the world. In this first question, so we have some data about the melting and boiling point. So we know that melting is to do with solid going to liquid state and boiling is liquid going to gaseous state. Whenever a question asks your melting or boiling point, it's always about two things. Number one, what is their structure? Number two, what exactly are you breaking? So we're talking about the boiling point specifically, why the boiling point is different. So if we look at the boiling point, we can see that bromine is much lower. Bear in mind that this one is given in Kelvin, and then to convert to degrees Celsius, you do need to take away 273 Kelvin in order to convert the Kelvin temperature to degrees Celsius. Well, regardless, this is going to be much lower compared to this, whether it's in Kelvin or degrees Celsius. So why is magnesium a liquid over a much greater range? So it stays as a liquid before it boils. So before it boils, so we need to relate this to the melting point, going to the boiling point. Why is the range so big for magnesium compared to bromine? This must be to do with, going from the liquid to the gaseous state. It requires a lot more energy for the magnesium to go to gaseous state. So let's talk about structure first. So they've given us quite a lot of lines for 5 marks altogether. So the best thing to do with these kind of questions, even though it's essay based, well, the fact that it's essay based means it's open-ended. So we can say that magnesium, I've used a symbol there, but I could write it in full words. So magnesium has a giant metallic lattice structure. So how does the giant metallic lattice structure actually look like? So you will have consisting of your layers of positive cations, So your cations are positively charged, and this is in the sea of delocalized outer shell or valence electrons. So what is actually happening here is we gotta melt. So melting magnesium. So melting magnesium means that you need a lot of energy. And why is that? Because you need to break the strong metallic bond, which is the strong electrostatic force of attraction between the particle, which I've just specified before. This is between the cations and also your sea of delocalized electrons, your delocalized outer shell electrons, particularly, because that is how you would label it. Now in terms of silicon, no, it's not silicon. What they're looking for, bromine. So bromine, which exists as this diatomic molecule, they just have a simple molecular structure or simple covalent structure. So simple is not for bonding, simple is for structure. We specify as simple covalent structure, never simple covalent bond. So what do we have? We have discrete single molecules. Of course, they exist as individual single Br2 molecules of Br2, and then they have weak intermolecular forces in between. So between the molecules, we have intermolecular forces. So when we say melting, boiling, because we talk about boiling bromine in the questions. So boiling the bromine, talking about the boiling point, you require very little energy. Why is that? Because of its simple structure. What exactly are we breaking? We are breaking just the weak intermolecular forces. However, at A level already, we must specify this because this is element itself bonded to itself. There is no permanent dipoles. It is just London dispersion forces. And these are weak intermolecular forces, which I've just mentioned previously. Therefore, you require very little energy to break these. These are between the molecules. On to the last part where we have to justify this or contextualize our answers. So, boiling bromine require far lesser energy because you are just moving the molecules further apart, far lesser or lower amount of energy that having to melt then having to boil the magnesium, because it said magnesium is a liquid over much greater temperature. So we talk about boiling, then having to boil, i.e. liquid to gas for the magnesium, as we do need much more energy, much greater amount of energy, so much more energy is needed to break this much stronger. So this is about comparisons, about the relative strength of the metallic bonds. So the metallic bond is much stronger compared to the intermolecular forces, which is to breaking the London dispersion forces, the weak intermolecular forces. So state the structure, state what you need to break, and then compare the strength of what you are trying to break there. And that's it for that 5 marks question. This question number 2, macromolecule there. Macromolecule is a word that isn't very popular these days, but I guess it's still in the AQA syllabus. This is what we call the giant covalent structure. So it's a giant structure. Macro means big. So if we look at this word molecule there, it's suggestive of covalent bond, and we know that copper, being a transition element in the middle block of the periodic table, is also known as transition metal. So not molecule, not covalent, because it's a metal, so it has giant metallic structure, so A cannot be the answer. Silicon dioxide, the oxide of third period chemistry, so it's actually, this is the answer, because each silicate is bonded to 4 oxygens with 4 electrons in the outer shell, and that's how you complete your outer shell. Each oxygen with 6 electrons in the outer shell, group 16. Therefore, you want to form 2 covalent bonds. You want to share 2 electrons out of your 6 existing outer shell electrons to complete outer shell. And this is bonded to 2 silicon. You can think about shape, you can think about bond angle. So the silicon in return is bonded to 3 other oxygens. Altogether, 4 oxygen there. So around the oxygen, you have 2 bond pair and 2 lone pair. That is your nonlinear or your band geometry there, just like in water. And then we talk about around the silicon, we have 109.5 degree, because this is your classic tetrahedral geometry, where silicon is just below carbon, just like in diamonds, when the carbon form 4 covalent bonds to 4 other carbon, you got 4 bond pair and 0 lone pair, 4 bond pair repelling equally. This is in AS shape of molecule. The theory is called valence shell. In the outermost shell, compare how many electron pairs you have, bond pair, lone pair, that kind of concept there. P4O10 is not a giant molecule. Instead, what it is a simple covalent structure, and that is why the melting point of SiO2, very high melting point, but this one is much lower melting point, and it's not a giant covalent structure there. MgO is a giant ionic lattice structure. So again, it's not a molecule because it forms ionic bond. Ionic bond, courtesy of the ionic structure, cannot be a molecule there. Question number 3, silicon dioxide has a crystal structure similar to diamond. I've just drawn silicon dioxide SiO2. Give the name of the type of crystal structure. It's basically a giant covalent structure. Giant covalent structure or giant molecular structure. These days, people normally use giant covalent structure, but if you write down giant molecular structure, that is equally correct as well. Now, suggest why silicon dioxide does not conduct electricity when molten, because this is about covalent bonding, right? So we cannot be talking about ions. If the moment you talk about ions, that is when you lost the plot. So even when molten, we know that melting giant covalent structure means you break the strong covalent bonds. We do not simply have ions. We do not have free electrons. We do not have free ions, okay? Or ions. I did say ions are not acceptable simply because you don't form ions. So perhaps that is not a good word to use. We don't have free electrons to conduct electricity. Therefore, it does not conduct even when molten. And graphite is the giant covalent structure that can conduct, simply because graphite from your IGCSE days, they will have a layered structure where you have each carbon bonded to 3 other carbons. And if each carbon is only bonded to 3 other carbons, each carbon there will have 1 free electrons. So you have 1 free electron on each carbon, which is trigonoplanar, 120-degree trigonoplanar in the structure of graphite, and that is why graphite can conduct electricity, part of your IGCSE as well as O-level chemistry there. Part C, silicon dioxide reacts with HF, and you get these H2SiF6. Let me just move that a little bit so you can read the question. H2SiF6, write an equation for this reaction. We also form one other substance. So just balancing your equation as well. Do not forget that. React with HF. So I get H2SiF6. First thing I realize is there is 6 fluorine there on the right hand side. So I must have 6 fluorines by having 6 HF. And there's 1 silicon. There is oxygen. There is 1 silicon, so this must be 1. So there is 2 oxygen, O2. There is already H2 here. There is H6 here. So I just need 4 more hydrogen. But if I look at H4O2, that doesn't exist. So instead what happened is, what really I would have gotten is H2O. That one is a molecule of water that we know very well. And it seems like we have 2 multiples of water, because that will give us 4 hydrogens and 2 oxygen. So hopefully you will be able to see the remaining atoms. Not necessarily is a correct formula, so you need to be aware of how to balance your equation. That's it for the 3 marks questions, and I think I'll just leave it there for this structure and bonding tutorial. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Do follow me at ptet.chemistry on Facebook, Instagram, Twitter and Telegram to get connected, and get in touch at the country code +673, and then the number is 8656158. You can get a number from the video description as well. Get in touch for private tutoring where I can go through anything, questions or concepts of your choice. Thank you for watching again. See you in the next tutorial video.